A lot to learn. Is it on? Am I on? Super. So before I start, I just give the two TAs to give you a few comments about recurring problem they found in the homework.
So a couple of things that I want to mention to you guys on this next on this part two. But certainly follow directions. We talked a lot about stuff that was related, but never actually answered the questions that being asked. So we lost a lot of points. That's why. Also show your work. A lot of you guys just put down 4 numbers, and I don't know how you got those numbers. So if the numbers are wrong, I can't give you partial credit. So that's another place people lost a lot of points. And just as a reminder, we're both completely available via email. I'm on campus a lot, so if you want to come meet with me, I can meet you guys to help you with the homework. But if you get to a question and you're not really sure how to go about answering it, shoot me a quick email, how do I get started, where one of my work is here. Figure out how to get started on it, okay? So if your grades are not what you wanted for this homework, come see me, I can help you out and hand it back in next Monday and get some points back, okay?
For homework number 1 redos, it would be helpful. So some people didn't hand in their copy that in class, so it was just online. And if you don't provide all the answers, I have to go back and forth. So if you're going to do a redo, even if you got that answer right, you can say like I got full credit, or just leave it in there and don't change it. Then I can read it. Otherwise, I have to go back and forth with the document and make sure everything's labeled. Some people didn't, I guess, take all the comments. I thought I tried to provide as much detailed information as I could, and some people tended to ignore it. But so try and, it's all there for you. You have the correct homework and you have my comments to get those points. And for figure captions, a lot of you, who still has their writing about biology book? Chenik. Everyone go read how to write a figure caption. It seems like a lot of people wanted to start interpreting what the lines meant or what the data meant, and that would go in the results section. The figure caption is a standalone thing, so I would revisit or come talk to us. I'm happy to discuss how to do that with you. And I know Marina's here, but feel free to email me, and I'm happy. I know this might be awkward for you guys, but I'm happy to talk on the phone or Skype you guys if you really need help. I'm totally available to do that. So she's not available.
And same with me. You can send me email, and I tend to answer pretty fast, anytime.
If you don't like emailing on Thursday from like 8 to 3, I'll be in Estabrook 206. Feel free to stop by if you want to talk about it. Okay?
So just so you know, unit conversion are an issue. We talked about why we care about them. It will be in the homework, it will be and continue to be in the homework, and it will be in the exam. So the exam is in 2 weeks. The exam on the physics part. So it's going to be at the time of the class. We have one more class next week where we're going to talk about low Reynolds number, high Reynolds number, swimming of organisms. It's going to be a fun class and a fun lab. And then the next Monday is an exam. I usually do a review session the Sunday before. So I'll send you information about that. If it works for you, great. And I tend to bring pizza for that review session. So those who come get fed. And then we'll do the midterm, but there will be a lab in the afternoon. We'll do a lab on light and sound, optics and acoustics. So don't miss the lab. There will be a lab. Oliver, here is a, like this. There's seats over there. Okay. So today's topic is temperature and heat. What am I doing? Oh, it's like I'm not on that. Come on. Okay. Heat and temperature. We talked about the fact that temperature is proportional to the kinetic energy of the molecules. And that in the first law of thermodynamics, those of you who've taken thermodynamics anytime, claim the following. If two objects have the same temperature, when you if they have the same temperature, upon contact, they will maintain exactly the same temperature. So we know that heat is passing from one object to the other because upon contact, one of them is going to have a higher temperature than the other. So going back to that kinetic energy of molecules, there's this equation derived in the beginning of the 20th century where there's Boltzmann constant here. This is the temperature in Kelvin that relates, again, you don't have to remember equations of that sort. I mean, you have to remember just the basic ones that you can derive from unit. But this one tells us something about the relationship between temperature and kinetic energy of molecules. There's the mass is here. So the mass times velocity squared divided by 2. Here it's u instead of small v, but it's the same. 3 times this constant, which is the Boltzmann constant. Absolute temperature in Kelvin divided by 2. So now if you put into this equation the Boltzmann constant, which you can Google, the room temperature, 293 Kelvin, and the mass of a single atom of water, or molecule of water, it's not an atom, it's a molecule, what you'll find is that the average velocity is around 640 meter per second. Now, anybody here remember what's the speed of sound in meter per second? In air? About? Nobody? It's about 300 meter per second. So the speed of the molecule is twice the speed of sound. It's much faster than an airplane in the air. It's Mach 2, if you will. So they move very fast, not very far. But this is the oscillations due to the kinetic energies of molecules at room temperature. Very, very fast. But over very short distances. Now, heat and temperature are not exactly the same. Because as you know, in order to change phase from liquid to ice, or from ice to liquid, from liquid to vapor or to gas, we need to invest energy. And while we're investing that energy, heat is going in, but there's no change in temperature as that goes through, or the average temperature of the water. The average the heat we need to evaporate a gram of water is 540 calories. Calories are units that are very convenient for us because it's the unit that we need to increase the temperature of 1 gram in one temperature, 1 gram of water in one temperature. This is where it came from. So it's about 4.2 joules. For water, 1 calorie will heat just 1 gram of water at 1 degree at standard temperature and pressure, so around 14 degrees C to 15 degrees C. So this is why we use calories. That's where they came earlier. But in MKS, it's about 4.2 joules. So we need 540 of them to simply evaporate 1 gram from liquid to, change it from liquid to gas or evaporate it. Comparatively, we need only 80 to melt it. So move it from ice to, so it's about a factor of 6. More, we need 6, even more than that, more like 7, closer to 7, that we need for evaporation compared to. When we talk about heat, so the heat content, we have the mass of the object, something called the heat capacity, and then the change in temperature that we're trying to acquire. That's to warm a massive material by delta T, this is the amount of heat that we need. So this is, as we're changing temperature when you're in one phase, this is the amount of heat you need. The amount of heat to change phase is what we just talked about here. So this is the specific heat. And specific heat is very different between different material. As you know, water has a large one, much larger than the atmosphere, than air. So it plays a role in, for example, moderating climate, moderating weather. Places that are close to big water masses, or where the weather comes from the ocean, like the west coast of the United States, tend to be much moderated in climate compared to the east coast, where most of our climate comes from land and exhibit much larger temperature fluctuations. So it's important in this respect. Now the calories associated with food are not these small calories, they're kilocalories. There are 1,000 of these small calories, the 4.2, the one for 1 gram of water. So these are the ones when you see calories on your food, on your on the stuff you eat, these are the big ones, the kilocalories. It's about the energy to eat 1 gallon by 1 degree, or evaporate 2 grams of water, or melt 50 grams of ice. So a question to you. We're talking about evaporation, and I showed you the diagram here. But do we only evaporate at 100 degrees C? Does water has to get to 100 degrees to evaporate, or is evaporation occurring at other temperature? Ian? We know that we can dry clothes at room temperature. So it doesn't have to be 100 degrees to evaporate. So how can that be? What do you think is happening? We have a very large distribution of kinetic energies of molecule. Some of them are slower at any given time. Some of them are much faster. Those that are much faster can escape and become gas. So at any given time, particularly if there's the air around has such less humidity that there's no exchange back at the same rate as we take them out of the liquid phase. So you can dry clothes, especially in this weather where it's very dry outside, at much lower temperature than 100, because the tail of the distribution of the kinetic energy contains molecules that are vibrating much faster than the average. The temperature we talk about is the average kinetic energy of molecules. It doesn't describe the long tail of these molecules. So at any given time, we can get molecules escaping water to vapor, and vice versa. When it's extremely humid outside, we can get molecules that become, from vapor, change into becoming liquid. So that's important to remember. We saw that. Okay, so there's a 10-point extra credits today, just so you get a sense of how much work you can do with these calories. We said that energy is the capacity to do work. And it turns out the Hershey Kiss, the kind you're going to eat plenty next weekend, has about 26 kilocalories. And it turns out, if you do the math correctly, that it can provide the energy to lift an SUV about 2 meters in the air. The amount of potential energy that an SUV gets by lifting it to this height equals the energy in 1 Hershey bar, if you could extract it all. So there's plenty of energy. So now the question is, how come we are not able to eat 1 Hershey and raise a 2 meter off the ground? So there's obviously a structural issue with our body, but there's also the fact that the food we eat, we're not very efficient, and food web are not very efficient in extracting all the energy for it to just do work. Most of it is used for, in our case, to keep our temperature up, and so it doesn't necessarily transfer well, and some of it is just dissipated. So biomass is not transferred extremely efficiently. It's on the order of a few percent from one level in the food web or food chains to the next. We're not, the system are not very efficient in terms of transferring energy. This is why you need to eat much more than your body weight within your a generation time, etc. Okay, so we talked about the fact that we need to invest energy in order to melt and to evaporate, and vice versa happens when you go the other way around. So energy is released when you condense water, and how do we know it happens? For example, if we look at the temperature in clouds, there's actually a halo of warm temperature around clouds where condensation occurs. And similarly, when you freeze water, there's a release of temperature. Because molecularly, you need less energy in those stages compared to where they came from. Now, why do you think we sweat? What does that mechanism do? What does it allow us to do for our body? Why is it an efficient mechanism to lose heat? Because when our body sweat, that sweat will evaporate, and in the process of evaporation, it will suck heat out of our body. Okay? It cools us down, sweating. As long as it's exposed to particularly dry weather. If we're in a humid day, it actually doesn't help us as much. And this is why we feel that in humid climates that the heat is much higher. The heat index tend to be very high. If you live in New Orleans, in the same temperature as in the desert in Arizona, you'll feel it much heavier and much harder for you to support, because you're not the sweat, it does not cool you as much because you don't evaporate as efficiently as you'll evaporate in a dry climate. Okay, now another concept associated with this wind chill. What is this wind chill? You're here in Maine, okay, it's minus 15, but it actually feels like minus 30. How does that happen, Ian?
That's like increasing the effect of evaporative cooling.
It's you're absolutely right. It's not just evaporative cooling, any cooling. So what happens is when you're in wind, you feel your body loses heat faster. And it's the rate by which you lose heat is the wind chill. Now, if it was evaporative cooling, it could bring you actually below the ambient temperature. And wind chill, we don't think about it as something that can bring your body temperature below or temperature of a building below the temperature of the surrounding. You can only go down to minus 15, but you get there much faster. That's what the wind chill does. It's just the rate by which you lose heat. You feel as if it was minus 25 because you lose heat very fast. So in the process of evaporation of the ocean loses heat. And bodies of water near deserts are actually much cooler than you'd think they would be. So if you go to the Red Sea and you look at the temperature distribution of the surface, it maybe warms up to 24 degrees in the summer, degrees C. The Mediterranean, which is further north, is in a climate where the temperatures are not as high, can warm up to 30 degrees in the summer because it doesn't evaporate as much. It's much more humid, much less evaporation. So the temperature of a body of water depends a lot on whether or not it evaporates. And whether or not it evaporates depends on the masses of lands near it. So now if we think about this process in terms of the hydrologic cycle, when the ocean evaporates here, we lose a lot of heat to the ocean. Once we condense in the atmosphere, there's a release of heat into the atmosphere in the process of condensation. And then there's the actual temperature that's associated as we move things around, which we call advection and convection. We'll talk about it in a second. So atmosphere gets warmed through condensation. Ocean loses heat through evaporation. And in the process of melting ice, what do you think? So what did we say about melting of ice? We have to invent energy. Again, this energy gets either from the ocean or the atmosphere around, but because the ocean has more heat capacity, most of it comes out of the ocean in the process of melting. And in the formation of ice, the ocean gets the heat associated. Okay, so now we're moving to measuring temperature. We can measure temperature in many different ways. One of the classical one is the one I have here. And now you can't see at all the little bar because I put in ice. But if I warm water, how will the density change? If I warm it compared to, say, 4 degrees C. We started at 4, and I warm it. What happened to the density of water? Density decrease. And so for the same amount of mass, how will the volume change? Volume will increase. So if the volume will increase, and I'm in a jug here, I should see what happened to that fluid. It should occupy more space and therefore climb in my little straw. And we'll see that. Actually, I'll leave it here and you'll see it in a second. I can show it to you much faster with alcohol. Here are two, and you've seen those before. Can you see those climbing up? They climb up because the liquid is expanding, and then it starts boiling because its boiling temperature is much lower. So these are, what we're using here is the fact that the fluid density and its boiling point are just very different and are very sensitive to temperature. Now I'll put it back here. It's going to cool down and then go back down. What I hope you'll see with this one is slowly as I'm speaking, it's going to rise through the... So this is one of the classical ways to measure temperature. Simply looking at expansion of fluid. And what you want to use is a fluid that changes linearly with temperature as much as possible. So that's the old ways to do it. And it could be mercury, it could be something else. Nowadays, we use more and more, and you'll see it in the lab, we use electronic material that have a predictable change with respect to temperature. Thermistor is one of them. And in a second, I'll show you this little device. Many of you have seen it. People use it when they do, when they look for leaks. But you can also use it for atmospheric research. You can point it at a cloud and see the temperature of the cloud with it. And what do you think this is using as a concept? So here, if I do it on my hand, sorry, oh, come on. My hand is now at 32 degrees C, 33. The room in general is at 18.5. How can it know the temperature of my hand without touching it? Yes, well, let's... Infrared. So infrared what? Yes, so it turns out, and we'll cover it, we'll talk about it in a second a little more, that everything, every body, we call it black body radiation, everything radiates. And it radiates according to its own temperature. So by simply collecting this radiation in the room from objects, or if I'm looking for leaks of heat from a point, this is commercial. You can buy it at Home Depot. You can tell what's the temperature at that area based on the radiation coming here, because this looks at the infrared and the spectrum of infrared. So this is radiation. It's very interesting because it can travel through space. We get it from the sun. This is how we get heat from the sun. It travels through empty space and gets to us. And then in order for it to raise the temperature, it has to be absorbed. So for me to sit in the bask in the sun and warm up, I need my skin to actually absorb that radiation. Then there's another mechanism by which heat is transferred. And that's conduction. That's if I touch something cold, heat is getting lost from me and heat is getting gained by that object. That requires contact. And finally, we talk about convection and advection. People use different terms. We'll talk about it in a second, which has to do with the fact that fluid, either water or air, can take heat from one place and take it somewhere else. If we talk about the Gulf Stream takes heat from the tropics and transfer it to Western Europe, making it such that at the same latitude that we are, people don't have as much snow as we do, if at all, on the western side of England or Ireland or in France. They're much warmer than we are because of this advective process in which the Gulf Stream takes heat and brings it to them. Okay? So three mechanisms. One in which a fluid is involved. We also use it at homes. At homes, or even here, our heaters are down here. Why do you think the heater is down here and not up there? Because it's going to heat the air, and then the air will rise and circulate. And this will cause the circulation to happen in this room, which heats the whole room. If I put the heater here, I'll simply have hot air at the top. Nothing's going to come down because it's less dense than the rest. Okay? So we're using them to drive convection. Those of you who have convection ovens, the whole idea in a convection oven is to use movement of air, accelerate movement of air so that heat gets transferred much faster. So that's this one. Okay? Very important, these three mechanisms. So radiation, again, depending on the object temperature, it will radiate. This is frequency here, or wavelength in nanometers. So that tells us at what temperature do we get the maximum emission of radiation from an object. And here we get the amount, the brightness, how much we get out. So if we are the sun, temperature about 6,000 Kelvin, which is almost 6,000 C, it's 5,800. The maximum radiation is in the yellow. Indeed, when we look at the sun, we see yellow. And it's much more than an object that's at 3,000 Kelvin, still very warm, in which it's going to be 1,000. And it's further and further towards the infrared the colder you are, and you get less radiance. So by looking at this position with this type of device, you can detect what's your maximum radiation emitted from something, and then translate that into what temperature the object has. So humans at about 310 Kelvin radiates at 10 micrometer. That's the wavelength. We cannot see it. We cannot see it, but there are organisms that can see it. And they get attracted to us through the radiation we emit, like mosquitoes, apparently. So we did already the demo of radiation. And then the other thing that's one can consider it as being the luck, other will say it's intelligent design, has to do with the fact that our atmosphere is transparent to visible light, which is the light coming off the sun. So if our atmosphere was not transparent in this part of the spectra, sun radiation would not have made it to the Earth, and our eyes have adapted to use this radiation to sense the environment. Because this radiation coming from the sun is available, we can use with our eyes, we can see what's around us. So everything is adapting to these physical curves that simply have to do with the radiation emission from different objects. We'll do this convection demo in the lab. So what we also see is that, and this is, you've learned about it in oceanography several times, you learned about it in SMS100, you learn about it again at 302, is the fact that because we cool, we don't, but because there's more cooling happening in the poles and more warming in the equator, the cold water in the poles will sink down because it's denser as we suck heat out of it, particularly in the North Atlantic because it's very salty as it comes up. And that will replenish the ocean in this conveyor bed that takes about 3,000 years to make a full circle. So that's on average. Of course, not every molecule of water does exactly 3,000. Some will go faster, some will go slower. And this is very similar than what you'll get if you, this is for the atmospheric case analog. If you heat from below, this will be what's going to happen in the equatorial regions, and you cool from above and generate these, and the sides, and you'll generate these convection cells. So very, very much what's happening in the ocean. And that's very important, and it has, of course, climatic implication. If you, for whatever reason, if the Gulf Stream were to slow down, as in a recent movie, that could have very strong implication in terms of getting warm water to high latitude, which will make much more difference the temperatures between southern and northern latitudes. So these currents moving around heat, but it's not just the current, it's also the atmosphere, help a lot in terms of making the poles less cold than they would otherwise be, and vice versa, making the tropics much less hot than they would otherwise be. And both atmosphere and the oceans take part in this. It's about half-half in terms of the amount, and they do it more or less in different latitudes. We'll see that in a second. Now, about some confusing terminology. I talk about advection and convection. The engineers tend to call convections everything we talked about. The motion associated with that takes heat from one place to another. In the ocean, we tend to talk about convection only the parts that have to do with density changes. So indeed, we're taking water from surface down to depth, and vice versa, from depth to the surface through heat exchange. I mean, associated with gradients in heat. One example that I did not talk about is what happened in mid-ocean ridge near Black Smoker. You're warming up water, and that water will tend to rise. turns out it's not going to rise all the way to the surface. It rises to a certain level and then spreads out as it mixes with water around it. But that happens in the ocean. And so there's heat. There's a source of heat down deep. It's not very strong, but it's there. It exists. And at the surface, we mostly, where we cool, we can make denser water. When we warm, we just make a layer that's stable and stay near the surface. So these are important, just important concepts to remember. But remember that depending on what field you come from, convection or advection will be used differently. So conduction, again, as we talked about, has to do with molecules vibrating, passing their vibration to the molecule next to them, passing their vibration to the molecule next to them. In the process, they lose some heat. The one that started, it was warmer, and the other one gains heat and gets warmer. And then there's an equation that describes that heat flux. Again, it has to do with a gradient in temperature. The more different the temperature, the faster you're going to transfer heat from the warmer to the cooler object. If it's a rod made of, if you take a rod made of a metal and you heat it in one side, it's going to transfer heat through. Whether or not you transfer it fast, that depends on what you're made of. As I said, if you use a plastic rod, it has a much smaller coefficient of heat diffusion than something made of metal. And again, between metals, there's large differences. What matters is that diffusion coefficient, the cross-sectional area, and the gradient in temperature between the two sides. And water is much more efficient than air in passing heat. Now, if I think of a diver and you're in a wetsuit, what are the processes going on there that allow you, with a wetsuit on, to feel relatively warm, other than peeing in your wetsuit? What do you think? Why is a wetsuit efficient compared to not having one with you? Yes.
It's the layer of water that you trap next to your body.
Exactly. You have a layer of water in it. Initially, it's cold as it gets in, but once it's there, it doesn't get exchanged with the outside. So that part of water stays right next to you with your body temperature. What happens to your black body radiation? You radiate all the time, but that gets very efficiently absorbed by water. Unlike air, where this radiation can be propagated far enough that I can measure it through air, near-infrared gets absorbed within millimeters. So all that radiation that we radiate gets absorbed by the water against you as well, and that stays right next to you. And so you cool. That water stays next to you, so you get it back, if you will. You don't lose as much because it exchanges back with your body the temperature that you warmed it with by conduction. So there's conduction because you touch water. There's radiation that's absorbed by the water next to you. And the neoprene stops the convection. There's no continuous circulation of new water next to your body. There's some of it, but it's a lot damped by having that neoprene. Now, what happened in a dry suit? Anybody? Yes, Ian?
Just keep the cold water out and rely on a buffer air that
So exactly. So in a dry suit, what you have is air within it, and you're also dressed with clothes that keep that minimize exchange with the outside. So your clothes keep you warm, not because there's anything warm about them. A blanket doesn't warm you. That's the terminology we use, but there's nothing warm about a blanket. What the blanket does is minimize the loss of heat from your body, keeping the heat around you, by absorbing the radiation from your body, by minimizing convection. So flow of air that will take heat away from you. So notice the terminology we use. Same goes with big blankets with goose down in them. What they use is the fact, as in the dry suit, that air transmits very poorly heat. So if I have a layer of hair around me, air that doesn't move, that insulates me from the surrounding and keeps me warm. This is why a down comforter is much better than something made of cotton, for example, or because it's fluffy. There's a lot of pockets of air that are not exchanged with. There's no wind going through it. Just the same air that stays around you. and isolate you. This is also why a friend of mine was going hiking next weekend up Katahdin, asked me if I have a mattress that's inflatable, because those are better in isolating you from the ground underneath or the snow than if it was a piece of neoprene or something else. Again, air is an extremely good insulator because it transmits heat very poorly. It's always worthwhile thinking about these issues, especially living in a cold climate like we do. So where is conduction important in fluids? You know, the conduction, again, it's by contact. Passage of heat by contact. Obviously, it's where the convection or flow is weak. That happens right next to any body. So right next to me, because of the no-slip condition, the flow is very weak. It has to, because no-slip condition. So there's a small layer, we call it a boundary layer, which is where conduction, just a contact between water and a body, makes a big difference in terms of passing heat. So conduction dominates in those. They tend to be much less than a centimeter thick. So any place, and similarly in pore water, in sediments where there's no strong fluid motion, there can be motion, but it's really weak. So any place where there's no strong motion because something inhibits it, then conduction becomes important. And that's what happened in your neoprene suit or your dry suit when you dive. So if we have a cross-section of a river. If we, just to summarize all the different mechanisms by which heat is gained or lost by a water body in this case. So we have atmospheric radiation that can get absorbed because there's something of color in the water. What we see of color in the water usually is the rays that don't get absorbed. So if the water is green, or if your tree is green there, it's because the chlorophyll molecule absorb in the blue and in the red, but not in the green. So green is radiated, but the blue and the red get trapped in the water. We have some radiation that bounces off other things. We can have shading of this radiation if there's trees around, so less of it makes it in. Then we have simply the temperature the water comes up with. That's simply advection. So the water had a certain temperature upstream. It comes with that temperature as you flow down. You lose heat by radiation back out. Everything loses by radiation heat. Evaporation. That cools down the water. We talked about it. Conduction. If the land around it is colder or warmer, it's going to gain some heat through it. And finally, this is a tiny term, it's simply friction. So when you do this, you warm your hands. This is kinetic energy that's transformed to heat just by friction. It's small. Apparently, people this year just came up with a new budget that suggests that breaking wave do transfer enough energy that it's actually noticeable. Until recently, nobody took breaking wave, just the process of the friction associated with breaking wave as being an important thermal terms. Now there's a new paper out there that claims that just breaking waves themselves, the process of breaking wave, taking that energy and changing it into temperature through friction is important and is noticeable and measurable. So that's a new budgetary number that was not there before. So going back to the Earth, net radiation on the Earth, if we average over the globe, as I said, is mostly around the equator and quite symmetric from the sun. Most of it is on the equatorial regions, and we lose heat. The Earth loses heat in the poles. But since the poles don't get much colder than they are, and the tropics don't get much heater than they are, there needs to be a mechanism that continuously takes heat from equatorial regions and transfer it to the poles. So this is the net radiation, then there's what's absorbed, it has the same. And that is what emitted. So these are the loss due to infrared. So we lose in the equatorial less than we absorb, and we emit in the poles more than is absorbed and is transferred and is provided to it. So the only way this balance the only way this can be in balance over time, we don't see the poles getting colder, we don't see the equatorial region getting warmer, is if continuously there are processes passing heat from the equator to the poles. And again, those are done both by atmosphere and ocean, currents taking a large amount of heat through currents from tropical region, currents like the Kuroshio, the Gulf Stream, and similarly in the Southern Ocean. They transmit most of the heat from the tropics further north, and then in higher latitude, it's mostly the atmosphere that does the work. It's mostly winds that transfer heat to the poles, such that we get this balance. Just to give you a sense of how the big differences between water and air. Density of air is about 1,000th of the density of water. So it's for the same volume. I mean, yeah, that's density. So there's no. It's already taken into account. So if I took this is wrong. If I took a meter cube of water versus a meter cube of air, the ratio will be 1,000 in weight. In terms of their heat capacity per kilogram, water is 4 times more than air per kilogram. So now per mass. So it's about 4,000 more in terms of how much there is in a meter cube of heat of water compared to the atmosphere. So the whole heat content of the atmosphere, the whole of it, is equivalent to 2.5 meters of the ocean. And this is why the ocean has such a big buffer of energy. They can contain much more heat than the ocean. So than the atmosphere. But the atmosphere is very efficient in transferring because winds are much faster. You can have a lot of transfer in terms of its efficiency. If we look at water versus land, again, the density of rocks is about 2.5 times that of water, but their heat content is again about 1/4 of that of water. So overall, if I warm a rock, and when I warm a rock, I only warm the surface of the rock, I'm not going to get as much an effect on temperature as I do when I warm water. And the other thing with water is that I can, sunlight penetrates water. It can go, not in the red, but both the blue and the green can penetrate. If it's a clear water, it can go down to tens of meters. If it's a lake in Maine, it's maybe a few meters. But it penetrates down and warm a volume. While when you deal with sand or rocks, you only heat the top surface of them. And it can be very warm, as you know. You walk on the summer on the road, it can be quite painful for your legs, but it's only that surface, which means that that's also the surface that radiates back. In the ocean, when you warm subsurface of the ocean, those layers, when they radiate out by black body radiation, that gets absorbed locally, it doesn't go out of the water. So you're much more efficient in trapping that water. There is, however, in water convection that happens often at night. As the top layer is cooled, it's going to go down and get replaced by another layer. So there is cooling of some subsurface water, but it's not as efficient as what's happening in land. So you don't have these giant fluctuations of temperature you'll have in land between day and night, or if you've been in the desert, compared to what you get in water. Is that clear? Makes sense? Consistent with what you think you know. We'll play much more with it today. We talked about this. Greenhouse gases. So we're extremely lucky on this planet that we have greenhouse gases. If we did not have them, the planet would experience much stronger fluctuation between season and between day and night. What happened is that energy that's radiated, black body radiation, we said everything radiates, gets absorbed by clouds and by atmospheric gases. Once it's absorbed, they heat, they warm up, and they re-radiate because of their own temperature. That goes back to the Earth some, and some goes out to space. And that process, you can sum it several times, and it results in our average temperature being about 30 degrees C higher than it would be if we did not have an atmosphere trapping that heat that we radiate out. It's like having a blanket. It acts like a blanket, but not a blanket in the sense of convection and advection, but in the sense of trapping the infrared radiation that the Earth is emitting out to space. And that's very important. This is the reason why, if you look at the moon, the side of the moon that's not illuminated is significantly lower in temperature than the illuminated side of the moon. Order, I think, 40 or 50 degrees less, and inhabitable. In terms of temperatures that we would like to live in. Same would have happened to the Earth if we did not have an atmosphere. At night we'll be dropping down in temperatures to below freezing, and then at day it could go up significantly more. So greenhouse gases are good for us. Now, what's happening nowadays is that we're accumulating much more greenhouse gases than there were there before, with already doubled CO2. And what that does is potentially trapping significantly more heat than was trapped before, and that's something that is changing climate. And changing climate is good for some. I mean, if you live in Maine and you'd rather be in a tropical place, that might be good for you. But this is disrupting what is currently some sort of an equilibrium that was there before the industrial age. So greenhouses are good for us as a species. Whether the change is good or bad, that depends on who you are and what it does to this planet. But I just wanted to make sure that you understand that these greenhouse gases help as a blanket to mitigate large changes in. So finally, some question I really want you to understand. One is, do you know when the longest and shortest days of the year are? Anybody? Yes. June 21st, longest. December. When is the coldest day of the year? Kinda. We're right in this stretch. I mean, between now and about 2 weeks from now, we're going to experience the coldest temperature. Afterwards, it's going to go high. So how can that be that when shortest day of the year is December and coldest day is around end of February, maybe sometimes beginning of March? How can that happen? So the one way to think about it is you're driving a car. When you push on the gas, it's not when you go the fastest. It's when you accelerate the most. Same goes here. The shortest day of the year is when you lose the most heat, but you continue to cool down afterwards. The coldest day is the day where you're losing just as much as you're gaining. And afterwards, you're going to gain more than you lose. Okay? And same goes with the hottest. Hottest tend to be in Maine in August. They're not in June. Okay, this is very important for you to remember. And we talked about ocean and land heating and how they're different. Temperature and biology. Organism lose and gain heat. We talked about it. Direct absorption. We talked about loss through radiation out. Warm-bodied organism. There's huge advantages because enzyme can continue and work, but you have to invest huge amount of energy to keep yourself warm, which a cold-blooded organism does not need to do. Enzymatic reactions are all function of temperature, and they all have optimal temperature that one wants to keep. Swimming and brain performance are both temperature dependent. Heat and size. The smaller you are, the more surface area to volume ratio you have. You can simply write the equation for a sphere. It's simply 4 pi r cubed. R cubed, that's volume. The area is pi r squared. The ratio of area to volume is 1 over r. The smaller you are, the bigger the area to volume. And you lose heat by area, not by volume. It's your surface area that loses heat. So it's really, really, so there's a big advantage to be an elephant compared to a if you're a mammal compared to a mouse, because a mouse will lose heat much faster, and relative to its body weight will need to gain much more energy than an elephant, eat much more often. Wind chill we talked about. Hypothermia has to do with the fact that for humans in particular, or any other organism, if you sink your body temperature for too long, you just might, parts of your body will stop function as they were. And also remember that viscosity is a function of temperature. So on the globe, between poles, viscosity is about a factor of 2 higher than it is in the tropics. And so all processes associated with viscosity, associated with motion through fluid, change due to that. For small, particularly for the small Reynolds number, small organisms that have to deal directly with the effects of viscosity. Questions, comments? See you in the lab.